Okay, so I will give you a brief summary of what's in Data Release 1. I won't go into many details because there are going to be more detailed talks later on during this meeting. And as it was said, I will also take a look ahead at the next releases that we're planning for Gaia. Okay, so first of all, I should say I stand here on behalf of a large European team with also a few from outside Europe who have done all the work over the past 10 years to prepare the software, do the planning of the data processing, execute the actual data processing, much of it also happening here at ESAC, which is why we're having this workshop here. I just want to emphasize again what Timo said. It's been a very tough summer for all of us in DPAC. Lots of people didn't take any breaks, everything to get the data release in place on time. So especially for those of you working in Europe, if you run into one of your DPAC colleagues, please tell them how happy you are with the Gaia data. It's very important for them. It's a good motivation to keep going. And of course, keeping those of us who are doing the processing happy, that will deliver you the next data releases. If there's something you don't like about it, you talk to me or to Timo. But just tell your DPAC colleagues how happy you are about the data release. All right. Okay, so what's in the first data release? So you've already seen the image, of course, of the billion-star atlas that we put out, the whole sky out to magnitude 20.7. Not quite complete at the moment because it's still a preliminary release, but I think it gives you already a very nice, a very impressive view of what the Milky Way looks like when you take a telescope like Gaia with basically HST-like spatial resolution and just take images of the whole sky. The second component is the Tycho Gaia astrometric solution. These are the 2 million stars for which we added as a prior information the position from either Hipparcos or Tycho. And in that way we were able to derive 2 million parallaxes and proper motions for this subset. And of course, this is one of the most exciting products, although as we'll hear maybe later on during the science discussion, there's also a lot you can do with just the star atlas. We also have a set of variable stars for which we have released light curves and other information pertinent to variable stars. This is a modest sample of about 3,000 stars located right around the south ecliptic pole. And this area was observed at high cadence during the first few weeks of the mission. So these stars have typically 100 to 200 observations, which is not normal cadence for Gaia, but because of this special observing campaign, we were able to put them out early already. And so we have around 600 Cepheids, of which about 40 are newly discovered by Gaia, and I think around 2,500 are Lyrae, again with a couple of hundred newly discovered by Gaia. But you'll hear more about this from Laurent Ayer later during this meeting. And then finally, there's a small additional data set that we added later on, which is 2,000 positions of ICRF quasars. For these quasars, we made a special solution to actually check the quality of our main astrometric solution. And those positions are slightly better than the ones that are published in the main Gaia catalog. And they were used to do an analysis of the difference between optical and radio positions. And the nice result there is that there's probably no issue in making the link later on between the Gaia frame and the radio frame. And so this is if you're interested in this topic, that's available as a separate table as well from the archive. Okay, here's just a summary view of the contents of the catalog in terms of the magnitude distribution. So the light green line shows the overall magnitude distribution of Gaia DR1. And you should note that most of the stars are located between magnitudes 14.5 and 20.7. That's over 95%. And you can notice a tail towards very faint magnitudes. I think the faintest object you can find in the catalog is at magnitude 28. And obviously these very, very faint objects, these are just processing errors. So we don't think we actually have observed objects at magnitude 28. But if you process billions of photometric transits for a billion sources, you make some errors sometimes. So this will be fixed in the future. But as Timo mentioned, the completeness limit is at about magnitude 20.7. And of course, we do get sources a bit fainter than that because of the onboard magnitude estimation error. And we'll hear more about the photometry tomorrow. So the other two curves here show the distribution in magnitude of the Tycho stars and those in the Hipparcos subset. So these are the stars for which we have the parallaxes and proper motions available. And you will notice that at the very bright end of the survey, there are stars missing. And this is because of the difficulty at the moment of treating bright stars due to saturation effects mainly. Yeah, so also notice this discrepancy here between the Hipparcos and the overall DR1 curve. And those are Hipparcos stars for which we were not able to actually make the 5-parameter solution, but they are in the catalog with just the position and brightness. Okay, I won't go into the details of the astrometry. We'll hear more about that later on, but just to make one point. This is a very large catalog now, 1 billion highly precise positions, so 1.1 billion sources. And the typical uncertainty is up to 10 milliarc seconds. And this means that when you're doing a cross-match of your favorite other catalog against Gaia, you have to be a little bit careful. If you just insert the normal search radius, you will get many, many matches. And so you have to do some work to do this cross-matching properly. And of course also take things like proper motions into account. Now there are two maps here. On the left you see a map of sources that were already known to exist. They were included in the so-called initial Gaia source list, which is a list of sources that we use to bootstrap our own processing. So we did not start from a completely blank sky, but we started matching any transit of Gaia to already existing sources. So 685 million of those are listed now in the Gaia catalog, but we also have 450 million what we call new sources. And these are strictly speaking sources that we could not match against the IGSL. But the fact that most of them probably are really newly discovered by Gaia, at least in the optical, can be seen from the fact that they are concentrated along the galactic plane, which is explained by the fact that Gaia's resolution is higher than most of the ground-based surveys which served as input for the IGSL, in particular the old photographic plate surveys, concentrations in the Magellanic Cloud. And you can also see these stripes going across the galactic plane. And that's basically the Sloan Digital Sky Survey footprint. And of course, the quality of Sloan was a lot better, so we didn't discover as many new sources there as compared to other areas of the sky. So this makes it clear that probably a good fraction of these 450 million sources are really new on the sky. The overall reference frame of Gaia is at epoch 2015. Keep that in mind when you're doing cross-matching. It's aligned to the ICRF to high precision. And I already mentioned this about the quasars in the special solution. Okay, again, this beautiful image that was produced at the University of Lisbon, and maybe André will say a little bit more about how they did it. We had some discussion initially within the ESA, with the ESA communications team, which image should be released. There's also a flux-based version, but that looks just like any other Milky Way panorama. And here you can clearly immediately see this is a Gaia image. And so I think it was a good idea to use this one in the press release. So again, there are artifacts in here. I'll zoom in on a few of those later on. But in particular, along the ecliptic region, there's the combination of the way Gaia scans the sky and the data quality. So we did some filtering before putting all the data out. For example, one of the filters was that sources have to be observed at least 5 times before they're included in the catalog. And that leads to this striping in these areas along the ecliptic where you get underdense regions. Yeah? So the quality of the astrometry due to the geometry of the scanning is less there, and that leads to some sources not making it into the catalog. So be careful when you're interpreting this, especially when you're looking for large features like streams on the sky, which you can in principle do with this catalog already. Something like this is not a stream, it's just a reflection of the completeness in the catalog. So if you take a closer look at some areas, so on the right you see the same picture that Timo showed before of the rotation pattern in the proper motions in the Magellanic Cloud, now projected against the Gaia image in the background. This was produced by Johannes Salman at the request of someone who wanted to show it during a talk, but it's a very nice picture, I think. And over here, this is the region on the sky near the Orion constellation. And you can clearly see the Orion clouds actually outlined now against the backdrop of the stars. I think this is the first time that you can really see this in optical star counts, So you see the Orion A and B clouds, but you can also make out the outlines of the Lambda Orionis region. So this shows the incredible power in just this first release of going back to this very classical method of doing star counts. And of course, you saw that already in the richness of detail in the previous map in the dust lanes along the galactic plane. And these are two other examples. This is the M33 galaxy, the Triangulum, and here the Andromeda Nebula M31. And again, these are individual detections of sources in these galaxies. So you see very nicely the spiral arm structure outlined in individual detections made by Gaia. So an interesting exercise would be to see what we can make of when we have the proper motions of these stars that Gaia will measure, to see whether the quality is good enough to make any scientific study out of it. This was actually one of the things that was in the original proposal for Gaia, that you could measure the rotation of Andromeda, but of course the specs that we have now are not as good as they were back in 2000. But I think it would still be interesting, or at least fun, to look into this to see how well we can do. But still, I was very surprised the first time I saw this. You can just see them in these individual detections, these beautiful galaxies. All right, a few illustrations from the data release paper on the overall quality of the Gaia data. So on the left, you see two HR diagrams for stars that are in the Hipparcos catalog. And both of them have been selected to have parallaxes in either Hipparcos and Gaia that are better than 20% relative precision. This is about 40,000 stars. And over here you see the HR diagram based on the new reduction of Hipparcos from Van Leeuwen. And this is the HR diagram as produced by Gaia. And you can see, especially if you look at the red clump, that it's much more sharply defined than in the case of Hipparcos, which is already an indication that the parallax quality in the Gaia data is better. And if you look carefully, you will also notice that the main sequence is somewhat better defined at the low mass end, a little bit sharper in the case of Gaia than for Hipparcos. And here is when you select only stars in the Gaia catalog with parallaxes better than 20%, then you have almost 80,000 stars located in a volume roughly within 450 parsecs. And this volume over here only goes out to 280 parsecs. So again, also showing that the reach of Gaia is a lot larger thanks to the better data quality. Now to make this a bit clearer, that the definition of the clump and the main sequence are sharper, this is a cut that was made along the colors between 1 and 1.1 in B minus V. So you make a cut vertically through the diagram and you plot the histogram of the absolute magnitudes. And then you see the blue line is Hipparcos and the green is Gaia, and you see how much more sharply defined the clump is, so leading, of course, later on to much better luminosity calibration. And again, also in the case of the main sequence, you see that it's slightly better defined when you look at the Gaia data. And this is the HR diagram for all stars in TGAS for which we have parallaxes better than 20%. So that's 1 million stars now, right? With Hipparcos, this was of the order of a few tens of thousands of stars, and now in one go we have 1 million stars for which we have 20% or better parallaxes. This is also a very nice illustration of one of the nice features that we have in the Gaia archive, which is pre-computed cross matches. So we've already computed the cross match between the Gaia data and the two-mass catalog, and there is a table that tells you which match we think is best, the so-called best neighbor, but we also give you all the other matches that were found with Gaia, so you can refine by yourself if you like. But in principle, it's very easy then to combine these catalogs and do further analysis. And Paula Marese will talk more about this, I think, tomorrow, about the pre-computed cross matches. So now we have 1 million stars with parallaxes precise to 20%, and again, a large volume, or to about 600 parsecs. And in the future, the numbers are listed here, what we expect. So about 10 million parallaxes precise to 1%, which is out to about 2.5 kiloparsecs roughly. So that's going to be a fantastic data set to recalibrate all kinds of luminosities of stars and distance indicators. And if you're happy with less precision, if you're happy with 20%, there will be about 280 million stars that reach that level of parallax precision. So a lot more to come. Okay, then this was a very, very nice exercise to do, which was something that Andy Gould did already 10 years ago or so, which was to make an HR diagram where you basically color code the stars according to the value of their tangential velocity, with the blue points being low velocity stars. So these are typically young stars, as you can see, in the being located in the upper part of the main sequence. And as you move to higher and higher tangential motion, you gradually move from the young stars to the turn-off of the disk and then into the halo region. And you can clearly see that the halo stars are also a little bit offset towards the lower metallicities. Of course, there's no surprises in here. This is already well known, but it's a very nice illustration that you know, what we produced is of good quality. It clearly makes sense. Okay, then a few remarks on the completeness of Gaia Data Release 1. So a zoom in on the bulge region where you see this very prominent pattern of striping, which is a reflection of the way Gaia scans the sky, and there are also actual data gaps. And as explained in the data release paper, this is really a combination of how the sky was observed and how we did our data filtering. So there are actually holes here and there in the sky as seen by Gaia, but of course this will be fixed in future releases. Timo mentioned Omega Centauri. This is a zoom in on the Omega Centauri region. I think there's a few tens of thousands of detections, or a couple of 100,000 of detections in here. And you can clearly see in the central area that it looks a bit strange. You see some holes, you see some patterns. And this is a combination of the fact that the onboard resources are not enough to download at each scan every star, to observe every star. Plus the fact that we don't do very well at the moment in treating crowded regions. So very often in crowded regions, the readout windows of stars overlap, and when that happens, at this stage we discard them, we don't treat them, and of course that leads to missing observations. And again, this will be remedied in future releases, but right now, if you make studies of these very dense regions, don't be surprised if you see strange patterns in the completeness. We also have cases, for example, of open clusters, where one half of the cluster is basically missing from the data just because it happens to be on a boundary of a particular way a region was scanned. This here shows a histogram of the magnitudes in Omega Centauri, and you can see that the completeness really bottoms out already at magnitude 18, and there are some features also at the bright end related, of course, to the fact that you have data missing. I already mentioned that bright stars are missing. We also don't have the high proper motion stars, stars moving faster than about 3.5 arc seconds per year. This was a technical mishap when we constructed the input catalog and did the initial cross-matching. So again, this will be fixed. And there's a bit more detail you can find in the data release paper. Now, one thing also to keep in mind, and this is also described in the paper on the initial data treatment, is that we have a lot of spurious detections on board, in particular in this data set, this early data set. And this has to do with the fact that bright stars cause very large PSF spikes that extend over a large region in the focal plane. And those PSF spikes have ripples, and those ripples are picked up by the onboard detection system as actual sources. It cannot distinguish them from real sources. And here you see an example on the left of Sirius transiting the focal plane during two different times, the blue and the red. And you can clearly see how the PSF spikes cause lots of detections around Sirius that aren't real. Here's another example. When Saturn passes over the focal plane, it causes an enormous amount of these spurious sources. And there was a lot of work done by the team in Barcelona to get rid of these. So they built models of the PSF based on the data itself. And most of the spurious sources have been filtered out. But it may well be that a few of them are left in the catalog. And in particular, it could mean that in some cases, the photometry of a particular source might be thrown off because of this one spurious source that enters into the data set. So it's not a large fraction of sources, but if you make large-scale analyses, this is something to keep in mind. And again, you can find more details in the paper. Yeah. Okay. So Gaia Data Release 1, this has been stressed on many occasions already. It is preliminary, it is only the first release. It's great, the quality is excellent. I've had so far really only positive reactions to it, but keep in mind that it is preliminary, and that's illustrated in this diagram. So here you see on a logarithmic scale, the parallax error as a function of magnitude, where the red line is the prediction for what we should get at the end of a 5-year mission. The gray points are the Hipparcos catalog, the new reduction, where you see that it basically follows photon noise all the way from the bright to the faint end, which is a nice illustration that Floor van Leeuwen really got the calibrations under much better control when he did the re-reduction. And then for Gaia DR1, you see that the behavior of the errors is flat. Yeah, so it's the same parallax error basically for all magnitudes, which illustrates that we are systematics limited at this stage. And you can also see that there is still quite a way to go from DR1 to the final mission performance. Right now we are at a level of performance that we can expect towards the very faint end after the 5 years of mission. And so next, for the next release will be somewhere in between, so that will be based on 22 months of data rather than the 14 months we have now, and already be a major improvement. But we will always be limited by systematics at this very bright end. Okay, so let's have a look at what's planned for Gaia DR2. So it's targeted for the end of next year. The astrometry and photometry, as I mentioned, will be based now on 22 months of data, and it will be a Gaia standalone solution. So we no longer need the Tycho and Hipparcos priors. We can completely solve for the 5 parameters from Gaia data alone. And that means that in principle we have 5 parameter astrometry for all sources, although there will be sources which, due to how often they've been observed, etc., might only receive a 2 parameter solution. The broadband photometry will be released again, of course, G as in this release, but we will also be adding the colors, which are the integrated light from the 2 prism photometers, and the photometric calibrations, of course, will be improved, and in particular, we will provide passband calibrations, which for this release we haven't. Keep that in mind when you're working with the photometry and you compare to predictions. Those are based on the nominal passband, which is really different from the actual one that we have, and the documentation provides some photometric transformations to deal with that. And then finally, we'll also have the median radial velocities for the bright stars, brighter than magnitude 12, whichever show constant radial velocity behavior, and this should be in principle many millions of radial velocities. There will be more variable star results. So Cepheid and RLI will be there again, but RLI now all over the sky. We can in principle identify RLI with just a very few points on the light curve. So that should be really an exciting data set, I think, for galactic structure studies. But also things like long period variables, short time scales. We will exercise our exoplanet transit algorithms. So those are already implemented in the pipeline. And the idea is that in principle you can, whenever you see one, you can alert on it to make sure that people can follow it up while the predictions of the next transits are still accurate. Solar system objects results will be included for a subset of known asteroids, I believe around 10,000. And then finally, we will try to derive astrophysical parameters from the broadband colors, in particular temperature and extinction. Now, of course, everyone here knows that deriving that from essentially one color is very difficult because of this enormous degeneracy between extinction and temperature. But we will do our best, or at least publish a relation which, when conditioned on extinction, can give you an idea of the temperature of the star from its color. Okay, then finally a few remarks on future releases. So each release is a step up in precision, in accuracy, in also the number of sources that we have in the catalog, the types of sources, also the richness of the data. So it will increase in many different dimensions in terms of quality. Expect changes to the source list. So our cross-matching, that meaning the linking of observations to sources on the sky by grouping the observations, is improving all the time. And so you can expect that source identifiers will change, and your favorite source in one catalog might not have the same number in the next catalog. Of course, this is something that will diminish over the course of time when the matching stabilizes, but for the next one we expect significant changes. And we are looking into tracking mechanisms to make sure that you can trace whatever source you're looking at in DR2 back to what it was in DR1. And we also intend to provide access to all the previous releases. Epoch data will be available from Gaia DR4 onward. Of course, we already have epoch data at the moment. We already released light curves for a few variable stars, and this will continue to happen. But really massive epoch data sets will be available from Data Release 4. And all the epoch and transit data for all sources will be part of the 5th data release, which is currently the nominal end of mission release. But of course, we have all the we intend to continue on to 2023. What was very popular this time around was file downloads. So rather than using the archive, you just download everything in a flat file and work with it on your laptop or on your computer at home. We will not be able to support this for the next releases because it's just too much. But we will probably make selected subsets available for download. But the message here is basically you need to learn how to work remotely with data, make your selections, etc. And I think that's it. Yeah.
Thank you, Anthony. Stick to the time. We have time for a couple of questions.
Well, really just a comment. I wanted to say thank you for supporting the cross-matching and planning for watching that as you evolve, because I think that'll be very useful to the community.
Yep.
I wonder if you could comment on the schedule and the uncertainty in the schedule for the release of DR2.
So the schedule, the end of 2017 is based basically on our internal planning. So that's really, we're quite confident in that, but of course things may slip by a few months back and forth actually. But it's something that we are constantly watching with the DPAC project office. But yes, I cannot right now give you an exact date as to when we will release. But this is not, I mean, the processing is actually already underway since last summer. So the schedule is based on what we already know from what's going on in the data processing centers.
Any idea about the precision and accuracy of the astrometry in the upcoming second data release?
Yeah, so at the faint end, it should basically be more or less scale with the amount of data with respect to the end of mission. So 22 months versus the 60 months. And then at the bright end, it's well, hard to say at the moment how much really we will gain because of all the systematics playing a role.
Should I pick all my objects in DR1 and then just download the data when DR2 is released, or should I just pick them all from DR2?
I would encourage you to pick them now from DR1 and work with them. And then in DR2, if you're lucky, nothing changes. You have the same source identifiers, there's no problem. But if so, then if they do change, then we will support you in finding them back.
So the link to the previous naming is pretty straightforward then?
It's not entirely straightforward, but that's a job that we will take care of. Yeah.
It's time for maybe 2 more questions.
Sorry.
Wait for the microphone for the streaming.
Do you know any ballpark on how many of the stars in DR2 are going to have full astrometric solutions with the distances or parallaxes?
Maybe better if one of the Leonard is in the room, or Jose. Yeah.
Well, the idea is that all the stars in data release 2 will have the 5 astrometric parameters, but of course the signal to noise ratio for the parallaxes will not be useful for many of them. So exactly how many better than ratio 5, for example, is very difficult to predict. But it will be millions, many millions.